In this video, we're going to be looking at pH. pH is equal to the negative log of the concentration of hydrogen ions. It's the same thing as saying the negative log of the concentration of hydronium ions. pH stands for the power of hydrogen. It tells us how acidic or basic something is based on the pH scale that runs from 0 to 14, with 7 being neutral in the middle. So for example, if we have a solution of hydrochloric acid that is made to be 0.35 moles per liter, what is its pH? So we know that hydrochloric acid has 100% ionization. So if it's 0.35 molar hydrochloric acid, that means it's 0.35 molar hydrogen ions and 0.35 molar chloride ions because they are in a 1:1:1 mole ratio. So then we can just plug directly into the pH equation. pH is equal to the negative log times the concentration of hydrogen ions, the negative log of 0.35 molar. So on our calculators, we have to find our log button and put in the negative log of 0.35 is equal to 0.45593, etc. Okay, so our pH is 0.46. So it is incredibly low on the pH scale. It's got a pH that's below 1. It's very, very acidic. Next we have, what is the concentration of a sodium hydroxide solution that has a pH of 12.7? If we have a pH of 12.7, we know that this is a base. It's sodium hydroxide. It's a strong base. The pH plus the pOH is equal to 14. So if we are looking for the pOH, 12.7 plus the pOH is equal to 14. pOH is 1.3. And the same formula applies for pH as for pOH. pOH is equal to the negative log times the concentration of hydroxide ions. So if we're looking for the concentration of hydroxide ions, we have to take the opposite of the log, which is raising it 10 to the negative 1.3 is equal to the concentration of hydroxide ions. So we're going to put that in our calculator. It's the opposite of log. So usually it's just shift in your log button. So I have to go shift my log button. So that's 10 to the negative 1.3 is equal to 0.050. Okay, so that's the concentration of my hydroxide ion. It is also the concentration of my sodium hydroxide, again, because they are in a 1:1:1 mole ratio and they have 100% dissociation. I know that they have 100% dissociation or ionization from my acids because these 6 strong acids, hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, and perchloric, they are the ones that are strong, which means 100% ionization. These strong bases, all the group 1 and group 2 hydroxides, except beryllium, that's a weak base, they're always going to have 100% dissociation. So if it's one of these 6 acids or one of these bases that falls from here, I can just do these calculations exactly like I did in these examples because they are 100% ionized or dissociated. If it's not one of these acids, if it's a weak acid or a weak base, that's a much more complicated question involving Ka values.